Greetings. In this problem, we're going to go over using bond dissociation energies to calculate the enthalpy of a reaction. Then we're going to look at the combustion reaction of acetic acid. We recognize that the bond dissociation energies represent the energy to break a bond, so we need to identify the bonds. And to do that, we're going to need to draw Lewis dot structures. But first, we need to make sure that we have a balanced equation, which we don't. So we need a balanced equation. So we have 2 carbons here. We have 4 hydrogens here, so we'll need a 2 here. We need to balance the oxygen. I like to write above each species how many oxygens I have or need. I'll put a question mark for the need part. And I can see that I have 6 on this side, 2 on this side, so I need 4, so I will need 2O2. Now that I've identified, balanced the molecules and the chemical entities, I need to look at how many bonds are in each species. So acetic acid has the acetate structure with a hydrogen attached to it. And so this is our acetate with a minus sign, but for acetic acid we have a hydrogen here. And we often put the H in front to show that this is the acetic hydrogen. This is the one that functions as the proton donor. And these hydrogens here are tightly held. Now we actually have 2 oxygen molecules. So we need to count for the bonds of both of them. And if I look at this, I've got 9 bonds. I've got 1, 2, 3, 4, 5, 6, 7 in the acetic acid, and 2 here. So I'm going to add energy to break these, okay? And since enthalpy is a state function, the energy change going from reactants to products is independent of the path. Now the path I'm choosing is breaking all the bonds. Now I've made the atoms. I've got the atoms as broken apart. And I'm going to form these. And formation is the opposite of dissociation. So I need to figure out how many bonds I'm forming. And I can see that each carbon dioxide has 2 bonds, and each water has 2 bonds. So I'm forming 8 bonds. And if you think about it, this is breaking a bond is an endothermic process. You add energy. Therefore, from conservation of energy principles, making a bond is an exothermic process. So the amount of energy required to released when these bonds are made is the negative of their dissociation energies. So what we're going to do is we're going to add the dissociation energies of the things that we break, and we're going to subtract the dissociations of the things we make. And the differences between those is the change of reaction because it's a state function. Okay, so now I need to figure out what I've broken. So I'll look here and I'm breaking 3 CH bonds. So I need 3 times the dissociation energy of CH. I'm breaking 1 C bond. Now there are actually 2 OCO bonds. One of them is a double bond, and one of them is a single bond, and you should know which one has the higher bond order. The bond dissociation energy. The one with the higher order has the higher dissociation energy. So this number is bigger than this. And I also have a OH bond. So there should be 7 bonds here, 3, 4, 5, 6, 7. But I'm also breaking 2 of the O double bond O's. Now, these I've broken, these I'm going to make. So I'm going to make 4 D C double bond O's. But making them is the opposite of breaking, so I subtract the energy required to break them. Okay? And in the same manner, I'm going to subtract 4 times the dissociation energy of the OH bond, because I'm not dissociating it, I'm making it. You make products, you break reactants, okay? So this is our path, and I could just plug in my numbers, but I can simplify my work a little bit. I notice that I have a C double bond O here and a C double bond O here. Now this is worth making a quick comment on. Bond dissociation energies are approximate energies, and in reality, the energy of this bond is different than the energy of this bond, but we treat them the same, okay? So there is, these are approximate energies, as we say in the text, okay? So if I have one here and one here, 1 minus 4 is the same as 0 minus 3. So I could cancel one of these and cancel one over here with 3. Likewise, I have an OH here and an OH here, so I could cancel one of those and cancel one of those, and the difference is the same. Okay? Now I need to go look at my tables up there, which I wrote down on a sheet of paper here, and I have 3 times the dissociation energy of the CH bond, because there's 3 of these I'm breaking, and that's 411 kilojoules per mole of them. Okay, and 1 mole of this would have 3 moles. And I'm going to leave the units out because I want to keep the chalkboard neat, but we'll have to add them in later. Now I've got 346 kilojoules per mole of this bond, and I've got 358 kilojoules per mole of the CO bond, this one here. Okay, I'm not worrying about this one and this one because I had subtracted 2 of those, and I'm saying there's only 3 here and 3 here. In reality, there was 4, and there was 1 here and 1 here. Now, this is the energy from the acetic acid. I also have to account for the energy to break the 2 O double bond O's, which is 494 kilojoules per mole. Now, these are the bonds that I'm making, okay? In reality, I'm making 4 of these, but the difference, since one of them was over here, is 3. So I'm going to subtract 3 times the dissociation energy of the C double bond O, which is 749. And notice that making a bond is an exothermic process. It releases energy. Breaking a bond is an endothermic process. You add energy to break the bond. It all makes sense. And now I'm going to subtract 3 times the dissociation energy of the OH, and I have 459. Realize that I'm really making 4 of them, but I had broken 1 here, so I only have, and so since I canceled that one out, I only have to worry about 3 of them. Now I get out my calculator, and I come up with 699 kilojoules. Now in reality, if we call this the molar enthalpy of combustion of acetic acid, it's per mole of acetic acid, okay? As an enthalpy of reaction, the per mole is implicit, and it's also per 2 moles of oxygen, per 2 moles of carbon dioxide, and per 2 moles of water. These have to be in the gas phase, and yes, combustion is an exothermic reaction, and this makes sense. Okay, I hope that helps.